Hi everyone, I'm John Boprowski and welcome to my webinar on how to create perfect impulse models for SerDes channels. Please type any questions into chat as I proceed with this webinar. I'll have a questions and answers session at the end of the webinar. You can also email me with your comments and questions at johnb@serdesdesign.com. Why is this webinar needed? High-speed digital integrated circuits and serializer-deserializer systems have their physical layer modeled and simulated in a channel simulator. Channel simulators are designed to use IBIS-AMI models that are based on the IBIS specification. Many commercial channel simulation tools cost tens of thousands of dollars to lease or own. Today, the SerDes channel simulation technology has matured so that it is available for free using cloud-based tools at SerDesDesign.com. Included with the SerDesDesign.com tools are options to generate IBIS-AMI models from circuit data collected from SPICE circuit simulations. This webinar is to let you know about the process I've used for many years to create perfect impulse models for SerDes channels, and it's available to you for free. What is SerDesDesign.com? I created SerDesDesign.com to enable me to create and deliver IBIS-AMI models to 40-plus high-speed digital integrated circuit companies over the past 10-plus years. Over that time, I learned many processes that practically guarantee a better, more efficient, and automatic IBIS-AMI model building process using free tools. I learned how to create high-quality, low-cost IBIS-AMI models while avoiding the standard approach using high-cost tools. Along the way, I learned that expensive tools kill all chances you have of achieving low-cost, high-quality IBIS-AMI models. My tools are based on free tools, Microsoft Visual Studio, CMake, web browsers, HTML, and more. I learned that creating an IBIS-AMI model should be the last thing you concern yourself with when it comes to creating IBIS-AMI models. Focus on collecting the correct circuit data. And use automation. My tools rely on automation to generate models from measured and simulated circuit data. I learned how to escape the costly commercial tool trap that keeps most persons stuck in a permanent high-cost model creation situation. Many of my tools are available for free on the web at SerDesDesign.com with options to download and install local copies on your Windows PC. I'm here to share my learnings over the past 10-plus years and introduce you to the same SerDes channel impulse modeling I have used to create and deliver high-quality, low-cost IBIS-AMI models. What this webinar will show you. This webinar first gives an overview of modeling SerDes systems in a channel simulator. Then I introduce the process I use to create perfect impulse models for SerDes channels. Perfect means that the impulse model exactly agrees with the SerDes channel characteristics in the frequency domain. Perfect means that the impulse model has no high frequency aliasing beyond the maximum frequency of the S-parameters used to represent the SerDes channel. You will learn how to convert SerDes differential channels to perfect impulses. You'll learn how to convert S-parameter files to Causal S-Parameters. You'll learn how to enable any AMI model to correct a channel's impulse response that contains high-frequency aliasing. Finally, I'll show you how you can get the tools that I use to create perfect SerDes channel impulse models and use them on your own PC. Modeling SerDes systems in a channel simulator. Channel simulators are based on the IBIS Open Forum Standard, currently at revision 7.2. This figure shows a typical SerDes system block diagram to be simulated using a channel simulator. This block diagram is generic for any channel simulator, but each tool has its specific way to represent this block diagram. The constituent parts of this SerDes system include the following: transmit IBIS-AMI portions. The AMI portion typically contains a transmit equalizer, often in the form of a feed-forward equalizer. The IBIS portion provides a differential output to the channel. There's a transmit package, a channel, a receive package. These pieces represent the differential channel. Each part is optional and may be represented using S-parameter files. There's the receive IBIS-AMI portions. The IBIS portion has differential input from the channel. The AMI portion typically contains a receive continuous time equalizer, a clock and data recovery unit, and a decision feedback equalizer. A key channel simulator property to keep in mind is that it considers that the entire analog content, the green area in this figure, the total channel, between the transmit AMI portion and the receive AMI portion is linear and time invariant. As an LTI system, the entire differential analog section in the SerDes system is accurately represented by its single-ended impulse response. This key concept enables the channel simulator to achieve its fast simulation speeds. Creating a perfect impulse model for a SerDes channel. IBIS-AMI model generation from behavioral data was built into the SerDesDesign.com channel simulator from the beginning. I've used this process over the past 10 plus years, providing custom IBIS-AMI models to over 40 plus companies based on the circuit data that provided me. In today's webinar, I provide instructions on impulse response modeling for a SerDes channel. The total channel is shown on the left. It includes all the channel content from the transmit IBIS buffer through the receive IBIS buffer. Some of this content might be circuit elements like resistors and capacitors and so forth, and some might be S-parameter files. This total channel is modeled in the frequency domain up to the highest frequency defined in the S-parameter files. The equivalent impulse model for this total channel is in the time domain. Modeling S-parameters in the time domain. S-parameter data inherently has problems when used in time domain simulations. S-parameters, though measured on actual hardware or obtained from circuit simulation, are typically non-causal due to limited spectral bandwidth, discrete spectrum frequencies, and possible measurement noise. All time domain tools that use S-parameter data need to correct for these non-causal, non-physical effects in the S-parameter data to obtain a meaningful causal time domain representation of the frequency domain data. Typically, S-parameters for a SerDes channel are characterized to an upper frequency that is at least 2 times the Nyquist rate, but higher is better. The channel simulators typically use characterizations with at least 32 samples per symbol or higher. The resultant upper frequency content in such channel simulation signals is at least 32 times the Nyquist rate. Correcting S-parameter data. Causality can be forced onto S-parameters by forcing compliance with the Kramers-Kronig relation that state that the real and imaginary parts of a causal response are related by the following Hilbert transforms, where U and V are the real and imaginary parts of the spectrum and P is the Cauchy principal value. This works fine up to the maximum S-parameter frequency, but what does a channel simulator do to resolve the signaling frequency content at higher frequencies? Unfortunately, many channel simulators result in undesirable high-frequency aliasing in the region beyond the maximum S-parameter frequency. Beyond the Kramers-Kronig relations, SerDesDesign.com relies not only on using the Kramers-Kronig relations, but also on an extension to these relations beyond the S-parameter's maximum frequency. The Kramers-Kronig relation shows that the real and imaginary parts of a causal response are related. Similarly, under certain conditions, the magnitude and phase of a causal response are related. Such a relationship shows that the phase shift is obtained by integrating the product of the slope of the logarithmic magnitude plot with a weighting factor that decreases as the integration frequency is further from the evaluation frequency. SerDesDesign.com extrapolates the S-parameter magnitude beyond their maximum frequency and derives the phase in the extrapolated region from the magnitude response. The Anti-Aliasing Algorithm. The SerDes approach, called the anti-aliasing algorithm, converts S-parameter data to its equivalent causal representation while preserving the fidelity of the S-parameters up to their maximum frequency and eliminating high-frequency aliasing at higher frequency with no added delay and no additional filtering. This webinar discusses 3 anti-aliasing algorithm applications: converting the SerDes differential total channel to its equivalent perfect impulse response, converting S-parameter data to causal S-parameters, and enabling any AMI model to correct a channel impulse response that contains high-frequency aliasing. Total channel to perfect impulse. First, let's talk about converting a SerDes differential total channel to its equivalent perfect impulse response. For discussion, a SerDes system with 20 gigabits per second NRZ signaling, that's 10 gigahertz Nyquist, is used with a channel that is defined with S-parameter files with maximum S-parameter frequency of 20 gigahertz and with 7.5 dB loss at Nyquist, that's at 10 gigahertz, for a 20 gigabits per second NRZ signal with 32 samples per symbol. Comparisons are made between the SerDesDesign.com channel simulator, which has no high-frequency aliasing, and a third-party, popular commercial channel simulator, which includes high-frequency aliasing. Here are the resultant I-density plots. The I from the third-party tool is shown on the left, and the I on the right is from the SerDesDesign.com anti-aliasing algorithm process. As can be seen, the I-density without the anti-aliasing algorithm has high-frequency aliasing that makes the I unusable. The I-density with the anti-aliasing algorithm is much cleaner and usable. These impulse responses can be viewed in the time and frequency domains. The blue curves are with use of the SerDesDesign.com anti-aliasing algorithm. The red curves are from the third-party tool, which clearly shows the high-frequency aliasing in the time and frequency domains. S-parameters to causal S-parameters. Now let's talk about converting S-parameter files to causal S-parameters. This is done by using the free SerDesDesign.com Causal S-Parameters tool at this website. This tool uses the SerDesDesign.com anti-aliasing algorithm process for converting frequency domain data into causal characteristics in the time and frequency domain. Consider the same S-parameter based channel discussed earlier. It had a maximum frequency of 20 gigahertz with 7.5 dB loss at 10 gigahertz. The SDD21 differential channel characteristic will be evaluated. Using an inverse FFT, the equivalent time domain impulse response can be obtained and will have non-causal characteristics. The Kramers-Kronig relation steps that I use. Here's the S-parameters can be made causal by use of the Kramers-Kronig relations by taking these steps. Convert the input spectrum real part to the time domain. Make the time domain symmetrical about t equals 0. Convert the symmetrical time domain back to the frequency domain to obtain the real part of the spectrum. Make the time domain asymmetrical about t equals 0. Convert the asymmetrical time domain back to the frequency domain to obtain the imaginary part of the spectrum. Convert the final spectrum to the time domain to obtain its real impulse response, and convert this real impulse response back to the frequency domain to obtain the causal S-parameters. The impulse response without and with causality corrections are displayed with a log y-axis to highlight the lower amplitude impulse levels. The time domain impulse response in red does not have causality corrections applied, and this is for the original S-parameters. The response in blue has causality corrections applied using the SerDesDesign.com anti-aliasing algorithm. With causality corrections applied, the impulse in blue is 0 before the impulse's inherent time delay of 1 nanosecond and is 0 after 18 nanoseconds. However, the impulse in red for the original S-parameters clearly shows its non-causal characteristics. Here's the plot of the SDD21 characteristics in the frequency domain on the right. The one in red is for the original S-parameters. The one in blue is for the has causality corrections applied. When corrections are applied to the S-parameters, there is some deviation from the original characteristics at the higher frequency end. And this higher frequency end is for the maximum S-parameter frequencies. If conversions to 30 gigahertz and beyond. If one is interested in preserving the S-parameter characteristics even at their maximum frequency, then one can use the SerDesDesign.com Causal S-Parameters tool to extend the S-parameters to 1.5 times or more beyond the S-parameters maximum frequency. Here's a plot of the SDD21 characteristics in the frequency domain with extension to 1.5 times the S-parameters maximum frequency. The one in red is for the original S-parameters. The one in blue has causality corrections applied. The blue for causal S-parameters overlaps the red up to the original S-parameters maximum frequency of 20 gigahertz. Also, the blue has no high-frequency aliasing beyond 20 gigahertz due to use of the SerDesDesign.com Anti-Aliasing Algorithm process. The Causal S-Parameters tool can be used to convert any S-parameter file to causal S-parameters when the number of ports is 1, 2, 3, 4, 6, 8, 10, 12, or 12 ports. The generated causal S-parameter file can be downloaded for personal use. Causal S-parameters were generated for the original S-parameter file for use with the 20 gigabits per second NRZ signal with 32 samples per symbol. Then the generated causal S-parameter file was used in the third-party tool discussed earlier. With these causal S-parameters, the third-party tool channel simulation resulted in no channel impulse high-frequency aliasing, and the output I was clean with no high-frequency aliasing artifacts. AMI model high-frequency aliasing corrections. Let's talk about how the AMI portion of an IBIS-AMI model can correct for a channel impulse response containing high-frequency aliasing that it receives from the channel simulator. We have already talked about using the SerDesDesign.com anti-aliasing algorithm process to convert channels into ideal impulse responses and to convert S-parameter files to causal S-parameter files. In the IBIS-AMI models that I deliver to my customers, I include the ability for the model to apply corrections to the channel simulator impulse response when needed using the SerDesDesign.com anti-aliasing process. Corrections are often needed when the channel simulator impulse response has high frequency aliasing in the impulse it delivers to the AMI model. Consider this typical SerDes system lineup. Assume that the channel has at least one S-parameter file. Let HT represent the channel impulse response. The transmit AMI model will have input HT. The receive AMI model will have input HT convolved with the transmit AMI LTI impulse response. An AMI model with the SerDesDesign.com anti-aliasing algorithm is used to correct the channel simulator impulse response that contains high-frequency aliasing. The AMI model has a parameter called channel anti-aliasing FC. By default, this value is 0 and is not used. When it is to be used, then its value is set to the maximum S-parameter frequency. This should be greater than or equal to the signaling symbol rate. When used, the model will convert H of t by applying the SerDesDesign.com anti-aliasing algorithm process to remove any high-frequency aliasing. This is done with no additional delay, no additional filtering, and with a match to the HFT response in its frequency domain characteristic up to the channel anti-aliasing corner frequency. Consistency with all channel simulators. IBIS-AMI models that include the SerDes anti-aliasing algorithm process will give consistent simulation results among the different channel simulators it is used with. Commercial channel simulators in general will give an accurate representation of a SerDes channel up to the maximum S-parameter frequency, but they tend to differ in how they represent the channel impulse response at higher characterization frequencies. The SerDes anti-aliasing algorithm process converts the impulse response from different channel simulators to the same impulse response. Summary. Here at this webinar, I've shown you how to achieve perfect impulse responses for SerDes channels. Perfect means that the impulse response exactly agrees with the SerDes channel characteristic in the frequency domain. Perfect means that the impulse model has no high-frequency aliasing beyond the maximum frequency for the S-parameters used to represent the SerDes channel. In this webinar, you also learned how to convert SerDes differential channels to equivalent perfect impulse responses, how to convert S-parameter files to causal S-parameters, and how to enable any AMI model to correct a channel impulse response that contains high frequency aliasing and thus achieving a consistency among different channel simulators. Topic for further consideration. SerDesDesign.com tools that include the SerDesDesign.com anti-aliasing algorithm process that results in perfect channel impulse responses are listed here. They're available at my store. There's the channel simulator tool for a single channel system. This is the same as the free web-based tool on my website. No internet connection is required. It uses your PC's processors and your file directories. My IBIS-AMI model generation tool, it converts any included transmit and receive behavioral model to IBIS-AMI models. It's an add-on to the channel simulator tool. It includes the SerDesDesign.com Windows and Linux IBIS-AMI model development environment. There's the SerDes IBIS-AMI transmit FFE modeling tool. It treats the transmit SerDes FFE circuit as a black box. You collect circuit waveform data and differential output S2P data. The tool automatically derives the IBIS and AMI portions of the IBIS-AMI model. The AMI model automatically extracts the FFE gains and filtering properties from the circuit data. And there's the SerDes IBIS-AMI transmit receive CTLE modeling tool. It treats the SerDes CTLE circuit as a black box. You collect circuit waveform files and differential transmit output or receive input S2P data. The tool automatically derives the IBIS-AMI portions of the IBIS-AMI model. So check these tools out. Check them out on my own dime. I personally guarantee that you'll be successful using the Windows PC copy of my SerDesDesign.com tools. You have a full 30 days to put it to the test. After that time, if you see the value in it, then you can buy it. I only want you as a customer if you're 100% happy with your investment. Simple as that. My SerDesDesign.com premium tools come with a node-lock time-based license. Use the tools free for 1 month. After you're happy, then you can decide to purchase a 12-month lease. And ordering instructions for your free copy are available at this website, and see the link below this webinar presentation. Well, this completes the presentation content of this webinar. I'll end the recording of the webinar and spend time with you to address your comments and questions. Remember, you can also email me with your comments and questions at johnb@serdesdesign.com. Thank you.